Hi, everyone. Welcome to section 1.7. Today, we're going to be working on analyzing graphs of functions and piecewise defined functions, section 1.7. So last section 1.6, we talked about transformations of different types of functions. We are going to still continue to talk about graphs and how last class, when we talked about transformations, we had a transformation across the x and across the y. And when you were across the x-axis is if when you had a negative on the inside, sorry, a negative on the outside. So for example, x squared versus negative x squared. So whenever you had, so this is the positive x squared, and then we had the negative x squared. That means that it's reflected across the x-axis, and then across the y-axis is whenever you have the negative. Let me bring this down. Negative on the inside, just to refresh your memory. For example, if I have the square root of negative x versus the square root of x, that looks like this is the square root of x. And then if I reflect it across the y-axis, it's going to be the square root of a negative x. So see how it's reflected across the y? So that means something when it's negative on the inside or on the outside. And that also touches on something that we're going to be learning today, which is called symmetry. When you are symmetric towards the y-axis, you're substituting negative x for positive x, and you're still the same equation. So when you have symmetry across the y-axis, you're substituting x for negative x, and you still have the same equation. That's when you're symmetric across the y-axis. You're symmetric towards the x-axis when you change y for negative y, and you get the same equation. And lastly, you're symmetric towards the origin when you substitute both x and y for negative numbers, and you still get the equivalent equation. So what we're going to be doing today is actually looking and experimenting what happens when I put in negative x for x. Is it the same equation? Is it not the same equation? And if it is the same equation, it's symmetric towards the y. If you change the y for the negative y and it's still the same equation, then you're symmetric towards the x. And lastly, when you change both negative x and negative y for positive x and y, then you get the equivalent equation. That means you are symmetric towards the origin. So what we're going to be doing is looking at different types of functions like so. Determine whether the graph of the determine whether the graph of the equation is symmetric with respect to the x, y, origin, or none of these. So then here we have, so questions 1 through 4 are different types of equations that we're going to start substituting. So what we want to do is actually test them all. So first, I want to test symmetry across the y. So what do we know about being symmetric towards the y? So I have to change. So I have y equal x cubed. Now I need to change that to y equal negative x cubed. And I want to know if I get the same answer. So what happens when I have negative x cubed? I get negative x cubed. So here, this and this are not the same. So that means it's not symmetric across the y-axis. What happens, so that's the first step. The second step, now you're testing symmetry. So the next part is we test symmetry for for x axis. So that means I have y equal x cubed. Now I'm changing the y to be negative y equal x cubed. And I divide everything by -1. So y equal negative x cubed. Is this the same as this? No. So that means it's not symmetric towards the x-axis. So the last one is to test number 3. So we're going to have to do that for all of them. We're going to test symmetry across the origin. So what does that mean? I'm changing if I have y equal x cubed. I have to change x and y. So now I have negative y equal negative x cubed. So I have a negative y equal negative x cubed. Divide both sides by -1. Y equal x cubed. Oh, look. This and this are the same. So because they're the same equation, then that means that my answer is y equal x cubed is a graph. It's an equation that it is symmetric towards the origin only. So that's our solution. Because we saw it's symmetric towards the origin. Because we saw that we tested for the y, we tested for the x, none of them work, but when we tested across the origin, both of them are negative. It gives me back my original equation. So that's exactly what we're looking for. So our solution for number 1 is this equation, y equal x cubed, is symmetric towards the origin. And you'll have a Canvas activity where you're able to see that and play around with the graphs as well. Okay. So just experimenting is always a good thing to do. So now we're going to do the same thing we did for equation number 2, problem number 2. So again, I'm going to do it step by step. The first thing that I'm going to do is I'm going to test across the symmetry across the y axis. So that means I'm changing x. So if I have y equal x squared plus 5, then this is y equal negative x squared plus 5. So this is y equal x squared plus 5, because if I square it at an x, I still get the same answer. So see how these are the same? So then check. So this is symmetric towards the y. And we know how an x squared plus 5 looks like a u. So it's symmetric across the y. And then number 2, we're going to test across the x-axis. So that means I have y equal x squared plus 5. And now I'm changing the negative y. But what happens if I have a negative? If I divide everything by -1, I have y equal negative x squared minus 5. This and this are not the same. So this is not symmetric towards the x-axis. And lastly, of course, we do the origin, but we already kind of know what's going to happen because for the origin, I have y equal x squared plus 5. If I both have negative y equal negative x squared plus 5, this is still negative y equal x squared plus 5. Divide both sides by -1. I get y equal negative x squared minus 5. So again, it's not the same. So it's not symmetric towards the origin. It is only symmetric across the y-axis. So our answer would be y equal x squared plus 5 is symmetric towards the y-axis only. Okay, so we're going to do 3 and 4. So hopefully you guys are getting the hang of this. So first, again, I'm going to go over here. I'm going to do first, I'm going to test. And I should be using a tinier one. So number 1, I'm going to be testing. Let me make this a little bit less bigger, like so. Get rid of that. So first I have to test for the y-axis if it's symmetric. So if we have x squared plus y plus 1 squared equal 4, then I have negative x squared plus y plus 1 squared equal 4. So then here, negative x squared, it's still x squared plus y plus 1 squared equal 4. Then they're the same. So this is symmetric across the the y-axis. Because when we substituted x for negative x, that's exactly what we got. So let's try x-axis. Is it symmetric towards the x? So for that, we're checking x squared plus y plus 1 squared equal 4. That's now x squared plus now negative y plus 1 squared equal 4. And for that one, we know if we expand it out, if we expand this piece, this is going to be y squared. So if we have that piece, it's negative y plus 1 times negative y plus 1. That's y squared minus y plus 1, which is y squared minus 2y plus 1, which is not equal to y squared plus 2y plus 1 from y plus 1 squared. So this one is not symmetric because it's not the same. It's not symmetric towards that. Okay. And then, of course, the last one, we want to check if it's symmetric. Number 3, test for symmetry across the origin. But we already know the answer because we already know that the x failed. So we know that the x is okay, but not the y. So then plugging it in, negative x squared plus negative y plus 1 squared equal 4. This one is okay, but then again, this one would fail. So it's not symmetric towards the origin. So the only answer is exactly what we found, that it's only symmetric, towards the y-axis. Excuse me there, let me make that a highlight. It's only symmetric towards the y-axis. Okay. So similarly, we're going to do the last piece. So that last piece is, again, number 1, I'm going to test for the y-axis if it's symmetric. So if I have y equals the absolute value of x minus 2, now it's y equal the absolute value of a negative x minus 2. But what do we know about absolute values? Well, because it's an absolute value, the inside of any absolute value being negative, it's still the same because it's the distance away from 0. So this is the same regardless. So then, yes, this is symmetric. The negative inside, so for example, a negative 2 is the same as the absolute value of 2 because both of them are the same 2. Now for when we're testing towards the x-axis, that's different because we have y equal the absolute value of x minus 2 is now negative y equal the absolute value of x minus 2. And if we divide both sides by a negative 1, now I'm going to get y equal the negative absolute value of x plus 2, which is not the same equation. So it's not symmetric. So we already know it's not symmetric towards the x. So then automatically we know that it's not symmetric towards the origin either. But let me just show you really quick how that looks like. So y equal the absolute value of x minus 2. Now, if we want to do it towards the origin, I'm going to change both x and y. This is testing for origin. Both of them negative. Now, if I divide both sides, I'm going to get y equal negative x minus 2. But we know, sorry, this should be a plus. But we know that this is not the same as the other equation because this is y equal negative the x plus 2, which is not what we want. Okay, so then this is not symmetric towards the origin. So we are learning how to apply both x and y being negative and then making sure that, yes, I get the same equation. No, I don't get the same equation. Like so. Okay. So hopefully as we go along, everything is making sense. It's you're trying to understand everything and it's aligning with your homework. So then just making sure that you're able to successfully complete the section. So symmetry goes along into identifying even and odd functions. So you're an even function, so you're automatically an even function if you are symmetric across the y. So if, for example, I already know this one and the one up top, this one, they're both even functions because they're symmetric towards the y. We're going to have an odd function if we're symmetric across the origin. So on the top, we found y equal x squared plus 5 to be an even function because it was symmetric towards the y, and y equal x cubed to be symmetric towards the origin. So that means that so again, y equal x squared plus 5 is symmetric towards the y-axis, so therefore it's even. And then y equal x cubed, it's an odd function because it's symmetric towards the origin. Right here, we don't see anything symmetric towards the x, so only even and odd. So either you're symmetric towards the y-axis or to the origin. That's the only two. So therefore, we're going to start identifying whether each function is even, odd, or neither. So very similar to how we tested symmetry, even, odd, or neither. So how to check if it's even? Well, it's the same as checking if symmetric towards the y. It's the same. So how do we do that? So we have this equation, f of x, which is the same as y, which is equal to x to the fourth minus x squared plus 2. Now we're going to change that to y equal negative x to the fourth minus negative x squared plus 2. And we want to check if it's the same. So negative x to the fourth power, because it's an even power, negative 4, negative x, negative x, negative x, negative x, that's still a positive x to the fourth, minus, that's not going to go away, a negative and a negative give me a positive x squared, plus, and then the 2 is just going to stay as 2. So notice that they are the same equation. So this one is odd. So this equation, it's an odd function. So you can't be both, or you're odd or you're even. Okay. So hopefully, again, as I'm moving along, it's making sense and you're able to identify what's going on with each function individually. All right, so let's go ahead and continue. Now we're going to check the next one, odd, even, or neither. So for this one, I'm going to check, of course, if it's even first. Is it even? Well, that means y equal negative x cubed minus negative x plus 3. I'm checking, so I have to change x to negative x, and this gives me y equal negative x cubed. It's still negative x cubed, and then minus minus, that's a plus x plus 3. So then notice that they're not the same equation, so no, not even. So let's try odd. How do we check oddness? How do we know whether something's odd? You have to change both x and y to be, we have to change both x and y to check. So now it's negative y equal negative x cubed minus x plus 3. So then here I'm going to have a negative y equal negative x cubed. This is negative x cubed. This becomes a plus 3. Oh, sorry, plus x, like so. And then the next one is a plus 3. Now what happens if I divide everything by a -1? I get y equal x cubed minus x minus 3. Does this is the same as the original? No, because this is a -3 and this is a plus 3. So it's not the same. It looks kind of the same, but not necessarily. So then it's neither. So it's not odd, it's not even, so it must be neither. Now the last one here, number 7. We're going to try, of course, f of x is equal to x cubed minus x. This is y equal x cubed minus x. And let's try if it's even. How are we going to check if something's even? Again, we're going to check if something's even by substituting to be a negative now, x cubed minus a negative x. We get y equal negative x cubed plus x, which is not the same. Not the same as the equation. So it's not symmetric. It's not symmetric towards the y, therefore it's not even. What about odd? Is it odd? Is it symmetric across the origin? So to check if it's symmetric towards the origin, what do we have to do? We have to change both x and y to be negative. So if we have y equal x cubed minus x, now we're checking towards the origin. Let me use the pink. Negative y equal negative x on the inside cubed minus negative x. So this is negative y equal a negative x cubed plus x. Now all I have to do is divide everything by a -1. So this gives me y equal x cubed minus x. Okay, well it is the same as what I'm given. So then therefore, the equation up top, it's symmetric towards the origin because I get the same equation. So because I get the same equation, that means it is symmetric towards the origin, and therefore it's an odd function. So now the last pieces over here are to define 8 and 9 to just by visualizing, is it symmetric towards, is it even or is it odd? Well, if I notice here, this y-axis, notice that they match. So this side is symmetric towards this side. So this is symmetric towards the y-axis. So therefore, automatically, we know that this is an even function. Similarly, if we want to do that on the next one, if we put the origin, it's not symmetric towards the y, but it's also symmetric towards the x. So if we put a line through the x and a line through the y, we know that this side is exactly symmetrical to the other one. So this is going to be an odd function because it's symmetric towards both x and y, towards the origin. So right here, it's symmetric towards our origin. So therefore, it's an odd function. Okay, the next few slides, the next part of this section is going to be graphing piecewise functions. We're going to be talking about an integer greatest value function, just looking at functions themselves, and then we're going to move on to 1.8. So let's start by looking at piecewise functions here and how do we graph them. So the first thing we want to do is talk about what does it mean to be a piecewise function. So the piecewise function is a graph that is graphed by pieces. So your graph is defined at a particular x location, a particular domain. So the first thing that they want us to do is to look at this graph. So this graph is the x squared plus 1. And I know that because it's saying where my x is less than 0. So my 0 being less than 0 is on this side. So that means the graph that lives in that location is x squared plus 1. And then x minus 1, the linear term, is everything greater than or equal to 0. And we know it's this linear term, so it's x minus 1. So the first thing that they want us to do is evaluate f of -1. So they're saying x is -1. Where does that live? On the top function or on the bottom? So where do you want to plug it in? Where do you have to plug it in? Well, we know -1 is less than 0. So we're going to substitute it into f of x equal x squared plus 1. You can only plug it into that one because that's where it lives. So then f of -1 is going to be -1 squared plus 1, which is 1 plus 1, and that's equal to 2. So 2 is my answer. Now, what is f of 5? So 5 is greater than or equal to 0. So I'm going to plug it in into the x minus 1. So then this is f of 5 equal 4 minus 1, which is, sorry, 5 minus 1, because that's what I'm evaluating. I'm getting ahead of myself. So that's 5 minus 1, which is 4. So when you're evaluating, you need to know which function does the value lives in. Now the last one is the tricky one because it's saying x is equal to 0. But you see a 0 here and a 0 down there. The only difference is saying you're equal to 0. The only one that is actually equal to 0 is the bottom one. See how it has greater than or equal to? So that means I'm only going to be substituting f of x into x minus 1, the equation. So f of 0 is 0 minus 1, which is -1. And those are the corresponding points. So if I have -1, 2, I have 5, 4, and then I have the point 0, -1. And that exactly lies on that graph. So right now what we did in question 10 was identifying which function do I have to plug in the value for. So we're going to do that next on the next one down here. So first I have to check x being equal to 1. Where does that live? X equal to 3. Where does that live? X equal to 4 and x equal to 5. So x equal 1, it lives in what domain? Is it less than 2? Is it in between 2 and 4? Is it greater than 4? Well, it's less than 4. 1 is less than 2. So that means I'm going to plug in h. Now this is h of x. H of 1 is going to be the x squared plus 3. So that's 1 squared plus 3. That's 4. What about the next one? Where is 3? Is 3 less than 2? No. Is it in between 2 and 4? Yes. So that value is already given to me. You don't have to plug in anything. That's equal to 7. There's no x value to plug it in. But I know that between 2 and 3 is between 2 and 4, there's the 3 that lives there. So if you're between 2 and 4, your value is 7. You don't have to plug in any x value because you don't have something to plug it in there. Lastly, 4, okay, so this is interesting because x equal 4. Is 4 greater than 4? No, it's actually in between. So again, we're going to get 7 on this side. And lastly, h equal 5 is greater than 4. So we're going to substitute it into h of x. So we're going to have h of 5. Where does 5 live? 5 is greater than 4. So that gives me 2 times 5 minus 1. I'm plugging it into this equation. And that's going to give me 10 minus 1 or 9. And that's my answer right there. Just making sure that I know where am I plugging it in. That is the question on piecewise functions. The next few, we're actually going to graph these. So notice I have 2 different pieces. They're both, one is less than 2 and one is greater than 2. So we're going to have 2 different pieces. So the first thing, when you're graphing, I like to do it step by step. So the first thing that I want to do is identify my endpoints, and then stop sharing. 1 second. So the first thing that I want to do is making sure that I'm able to substitute my endpoints, and then I'll talk about what those are in a moment. But I'm having issues with the connection here. One second. It should show up in a moment for some reason. Let me try that again. And then it should work. Let's see here. Sorry about that. Let me try that one. And it's downloading. All right. So let's try this part. Perfect. Now it's sharing. Perfect. So now again, we want to identify the endpoints. So to identify the endpoints, I have to see what the endpoint is. So it's saying that my boundary point here is 2. So it's not equal to 2, it's less than 2. So that means it's going to be an open circle because it's x less than 2. It's a strictly inequality. So then I'm going to do, okay, well, what's f of 2 of 1/2 times 2 plus 1? This 1/2 times 2 is 1 plus 1 is 2. So this point 2 comma 2 is going to be an open point, open dot. So I have 2, 2, it's going to be open like so. And then we're going to have a line that goes through the left. So I know it's going to go something like this behavior, something that's tending to 1/2. So then I'm going to test another point, maybe f of 0. What happens at 0? I know 0 is less than 2, so that's going to substitute into 1/2 times 0 plus 1. That's 1, so it's 0, 1. So my graph is coming from this direction. I could do maybe a -2, f of -2, negative, 1/2 times -2 plus 1, it's going to be -1 plus 1, which is 0. So at -2, I'm at 0. So I know that my graph is tending towards this direction. It's coming from here, and it's going to stop at the 2 right here. This is an open dot. Now, where am I going to get a closed dot? Well, now I have to plug in the other endpoint. So the other endpoint is also at 2. So this one, though, because it's a greater than or equal to 2, it's going to be a closed dot. So I'm going to do what's f of 2. Now, of the other equation, negative x minus 1. So that's -2 minus 1, that's -3. So the point 2, -3 is going to be a closed dot. How do I know? Well, because it's an equality. It's greater than or equal to. So I'm going to go into 2, -3, 1, 2, 3, and that's going to be a closed dot. And then I want to see where is this graph going to? It's going to greater than or equal to 2. So that means my domain, the value that I can pick, it's something greater than 2. So I'm going to plug in 3. So f of 3 is going to be -3 minus 1, it's -4. So 3 and down 4, it's another point. If I plug in f of 4, it's going to be -4 minus 1, which is -5. So -4, -5. So my graph is going to go this direction. And there's my graph. It's going downward. Because it has a downward slope, a -1. This one has a positive slope, the 1/2. And then notice how one is open and one is closed because it's open. It's open here because it's not, you can't So at 2 is going to be an open circle because it's less than 2. So it's not defined at 2. But this one is defined at 2 because you're greater than or equal to. So here we only see 2 graphs that corresponds to these 2 functions. So just making sure you add additional points so then you can see the behavior of the graph. That's really good. All right, how are we doing so far? So we had 2 equations. Now this one will have 3 equations because we have 3 different functions. So we're going to have 3 different pieces. The functions corresponds to the pieces. All right, so let's continue. And so we're going to see how many endpoints. So we have 0 as an endpoint and 2 as an endpoint. So the first thing we're going to see is z of x is equal to -1 when x is less than 0. So all the values, so the point -1, that's the y value. The x value is 0, so at 0, -1, you're going to have an open circle. So 0, -1, I'm going to have an open circle. And everything to the left is still -1. So all this is y equal -1, or z of x. Let me change that. Z of x is equal to -1 everywhere to less, where x is less than 0. But at 0, you have an open circle because you're not defined there. Okay. And I know it's a horizontal line because it's z of x equal -1. Now the next one, z of x equal x minus 1, it's everything in between 0 and 2. So here I have 2 different endpoints. So I have to substitute those endpoints. So then here I'm going to do z of x is equal to x minus 1, but one of them is 0, the other one is a 2. So then I have to do what's z of 0, 0 minus 1. And then I have to be equal -1. Okay, so this is going to be a closed dot. So 0, -1. Oh, but I thought it was open, I know. But we're going to go into the second one, and that's going to be closed. And then what happens at z of 2, it's 2 minus 1, which is 1. So at the point, that's also closed because it's defined. It's actually equal to. So it's closed dot from, it's the point 2, 1. My x is 2, my y is 1. So then it's 2, 1 right there. It's a closed dot. So my graph is from here. It only lives at this piece, the blue piece. And then the pink, the last one, z of x, it lives anything greater than 2. So z of x of -2x plus 6. I'm going to do an endpoint, z of 2. It's going to be -2 times 2 plus 6. -4 plus 6. This is going to give me a 2. But this is going to be open. So at 2, 2, let me go back for a moment. So this blue one was a closed dot and a closed dot. And then the pink, the new graph at 2, 2. So at 2, 2 is going to be open. And then what's going to happen if I plug in something greater than 2? So for example, C of 3, it's going to be -2 times 3 plus 6. So that's going to give me 0. So 3, 0 will be my other point. So I know that my graph is going to go downward. And that makes sense because my slope is a -2. So I could plug in another point, but maybe 2 points are enough. So 1.2 points, 1.2 points, and that's it. And that are, these 3 pieces correspond to my piecewise function. So there was a gap right there. 0, -1, it started as an open circle, but then it became a closed circle because of this reason. So then open and closed. All right. So the closed will always dominate the open. All right, and then we only have one more, a few more slides to go. And that is going to be the end of section 1.7. So for now, we're going to take a minor break and then we'll come back for part 2. All right, thank you.